application of derivatives. Yes, that's what we have today. We are going to study what is the application of differentiation of derivatives. How do we understand exactly when is differentiation or derivatives applicable? Let's take a function. Say y is a function of x, is a curve. If I plot this on the graph where this is x and this is fx, this is the graph, say for example, it's a parabola, it's a parabolic curve. The first thing, when we are talking of this function and differentiating it, what exactly we say? Differentiating y with respect to x. The term goes as dy by dx, that's f dash x. So we have been taught that when we differentiate a function, when we differentiate that fx, it becomes dy by dx and the function is denoted as f dash x. That means the derivative of fx is taken to be as f dash x. What exactly is dy by dx? What do we exactly mean when we talk of dy by dx? It's the differentiation of y with respect to x. Now, I'll give you a proper idea about what that dy by dx means. Dy by dx means the incremental change in the value of y because of a small change in the value of x. Dy by dx has been defined as the incremental change in y because of a small change in x. That means we intend to measure the change in the value of y because of a very small change in the value of x. That means if this is the initial value of x as x0 and the corresponding value as y0, if there is a very small change in the value of x, say here, it becomes x1, and we say that the value of y also decreases or changes to y1. Now this is suppose delta x and this is nothing but delta y. So incremental change in the value of y because of the change in the value of x. That means dy by dx is nothing but the change in the value of y because of the change in the value of x. Or we can also write it as y1 minus y0 divided by x1 minus x0. Now if you remember, at the secondary level, we used to study the same formula for the slope or the gradient of any straight line. So this is the slope or the gradient. So dy by dx can be also considered as nothing but the slope or the gradient of the curve. Yes, that's what we have established from here. The incremental change in the value of y because of a very small change in the value of x, that's dy by dx, or it is nothing but delta y by delta x, or it is change in the value of y because of the change in the value of x. Yes, so that's the first application of derivatives we learned. Dy by dx can be considered or is taken as the slope or the gradient of that particular function or that particular curve or that particular straight line. See, we can have a very simple example to understand this. If I have a straight line given by the equation 2x plus 3y equals to 10, we intend to find out the slope of this particular line. Now there are two ways. One, by the simple concept of coordinate geometry, That means we express it in the form of y equals to mx plus c, and m will denote the slope. So, can I write 3y equals minus 2x plus 10? So, y will be minus 2 by 3x plus 10 by 3. Now, that's the slope, correct? But this slope has been calculated with the concept of coordinate geometry. Now, if I differentiate this function, let's see whether it is applicable for differentiation or not. So, 2x plus 3y is 10, differentiating with respect to x, 2 plus 3 dy by dx is 0. So, dy by dx is minus 2 by 3. Yes, that's it. So, that is the slope or the gradient of a function or a curve or a straight line. Correct. So, that is our first derivation for the day, where we have seen that the dy by dx term actually calculates the slope or the gradient of that particular function. Now, we take on from here. So, we have seen that the slope or the gradient is dy by dx. The slope or the gradient is dy by dx. The slope or the gradient is dy by dx. That means if that's the curve x and plotted against fx as this. Now, slope or gradient. Now, let's start thinking once again. So, we have said that the slope or the gradient. So, after that previous discussion, I can simply write that the slope is dy by dx, which is f dash x, correct? A very important question comes is, what do we mean the slope of a curve? Now, that's not a straight line. We are accustomed with considering the slope or the gradient phenomenon for only a straight line. Now, what do you mean when you say that slope of a curve? What exactly do you mean when you talk of slope of a curve? Now, there's a very important definition. We all should know that when we talk of the slope of a curve, we mean that at any particular point, say for example this P denoted by x1, y1, and the slope of this curve is nothing but the slope of that very tangent which can be drawn from that point to the curve. So, the definition is a curve cannot have a slope. The slope is still meant for a straight line only. But once we talk of the slope of a curve, we mean the slope of that tangent which can be drawn from that point from the curve. So, if we have innumerable number of points on the curve, there are innumerable number of tangents and there are innumerable number of slopes. Yes. So, the term becomes very important when we talk of the slope or the gradient. Slope at a given point, say x1 comma y1. Yes. Because here we are talking about this, and it's not going to be the same when we talk of another point q whose coordinate is x2, y2. Yes. So, the slope of the curve at the point P is different than the slope of the curve at point Q, because both P and Q have got different tangents. That is the second important thing we should know when we are studying the application of derivatives. In general, people think that a slope is for a curve. That's a wrong idea. Still, a slope is only for a straight line. When we talk of the slope of a curve, we actually mean the slope of that very tangent which can be drawn to the curve from that particular point. So, if there are innumerable number of points, there are innumerable number of tangents. If there are innumerable number of tangents, there are innumerable number of slopes or gradient. So, the term becomes relevant when we are writing that point at x1, y1. So, that was the slope or the gradient phenomenon for differentiation. Yes, we have to learn how to calculate the slope or the gradient, that's dy by dx, and then we need to understand that the slope or the gradient at that particular point will be different from the others, and what the other thing remains is the equation of that tangent. The equation of the tangent T1 which we are talking. The tangent T1 passes through the point x1 comma y1. So we can write it as y minus y1 equals m into x minus x1. Yes, we have been taught as the equation of a straight line where x1 and y1 is the point and m is nothing but the slope which is already been calculated as dy by dx. So m equals dy by dx, which is slope. So that's the second application we have learned. First, what exactly is the slope or the gradient and how do we calculate the slope of the gradient? And number two, how do we calculate the equation of a tangent of a given curve at a given point, of a curve at a given point. So these are the two important applications which we have seen till now. The discussion continues that dy by dx can further give rise to different phenomena, can further help us to understand some different parts of application. Now what is that? So slope or gradient is dy by dx and that's the equation of the tangent. And at the same time the concept of slope is not meant for the curve but rather it's the tangent which has the slope and it is the tangent which indicates the slope of that particular curve. Now comes how do we apply it for the concept of maxima minima. We are planning to understand the concept of maxima minima for the same curve y equals to fx. Now again we start, we have already seen that the slope or the gradient is nothing but dy by dx which is f dash x, correct? Let us divide the curve into three different parts, three segments, one from A to O and the other from O to B. Now in the region of AO, the slope is negative, that is dy by dx is less than 0, correct? The slope is downward and the first order derivative is less than 0. While in the region of OB, the slope is positive, that means dy by dx will be greater than 0. So we are seeing that this is the region in which the curve is downward sloping, that's dy by dx is less than 0, and in the region of OB, dy by dx is greater than 0. What? At point O. It's neither decreasing nor increasing. It's neither downward sloping nor upward sloping. Now that point is called the stationary point and we can very well understand that the criteria will be dy by dx will be equals to 0. Yes. So if the slope is less than 0, we call it as the decreasing part of the function. If the slope is greater than 0, we call it as the increasing part of the function, and the point where that slope is equals to 0 is called the stationary point. Is called the stationary point of the function. Now that stationary point, if you look at the curve, it's nothing but the minimum point of the curve. So to understand the concept of maxima minima, we start our discussion from here. The curve would have been of this form and we take the same thing in this region dy by dx will be greater than 0. In this region, dy by dx will be less than 0, and again at this point is where dy by dx is equals to 0. So from this we can clearly understand that dy by dx equals to 0 is the criteria for the stationary point of a curve, and that stationary point can be two. One, it's either the minimum point or the maximum point. That means if dy by dx equals to 0, it's called the stationary point, which can either be the maximum point or the minimum point or the maximum point. So that's the first order criteria for a function to be maximum or minimum. When we intend to find out the maximum or the minimum, that's the maxima or the minima of a function, the first criteria is dy by dx equals to 0. So suppose, for example, if I have a function which is x square equals to, or y equals to x square minus 3x plus 5 given by this particular curve. Now the first thing, the slope, which is dy by dx, which is 2x minus 3, correct? Now putting dy by dx equals to 0, that's 2x minus 3 equals to 0, we have 2x equals to 3 or x equals to 3 by 2. Yes, that's the point where the curve is either at the maximum point or the minimum point. Now the second important thing comes is, how do we understand where is the curve maximum or minimum? That means this point 3 by 2 is the stationary point, yes, but the confirmation about whether it's the stationary point or whether it's the minimum point or the maximum point is yet to be decided. So what we do is, we go for the second order derivative. So find d2y by dx2, that's f double dash x. That means from here d2y by dx2 will be 2, the differentiation of dy by dx. Now if d2y by dx2 is greater than 0, the point is termed as the minimum point. And if d2y by dx2 is less than 0, the point is termed as the maximum point. So that's the second criteria for a function to be maximum. So the first criteria actually helps us to understand the stationary point, and the second criteria helps us to decide between the maximum or the minimum. Yes, it's greater than 0 for the maximum, a minimum, and it is less than 0 for the maximum point. Now we have to sum up the entire discussion. Like if we intend to find out the maximum or the minimum of a function, so that was the second criteria, when the function will be exactly decided as the minimum point and the maximum point. Now let's sum up the entire discussion. So once we intend to calculate the maxima or the minima of a function, once we intend to calculate the maximum or the minimum of a function, let's see what are the steps of calculations we have. So y equals to fx is a function which is given to us. So what's step 1? Find dy by dx, which is f dash x. What is step 2? Put dy by dx equals to 0 and solve. Now that is the first order criteria for a function to be maximum or minimum. That means for maximum or minimum, when you solve the value, you are expecting say x equals to a and x equals to b, say for example. So we are sure that at one of these the function is maximum and the other the function is minimum. If you want, we can have a graph which illustrates both maximum as well as minimum point. Now look at that. So that has this as the minimum point, say x equals to a, and that as the maximum point, say x equals to b. So we are expecting two different values, that is x equals to a and x equals to b. But again, who will exactly let us know that at which point it is maximum and at which it is minimum? So we go for the third step. That third step, find d2y by dx2, that's the second order derivative, which is f double dash x, and eventually put x equals to a in f double dash x. That means in the second order derivative, put the first value. If it is greater than 0, the function is minimum at x equals to a, and again put x equals to b in f double dash x, and suppose it is less than 0, so fx is maximum at x equals to b. That means this is the point of minimum and that's the point of maximum. Now minimum fx, that's minima, is nothing but minimum fx, which is nothing but fa. That means this value, and maxima, which is maximum fx, which is nothing but fb. That means it's this value. So that is the complete steps for calculating the function of the maximum or the minimum of a particular function. The first order criteria and the second order criteria. Now certain care has to be taken once we are calculating this. For example, if we only get one value of x, still we need to find out the second order derivative to decide whether it is the maximum point or the minimum point, and accordingly the other one does not exist. Say for example, if I only got x equals to a, the function is minimum and the maximum of the curve does not exist. That means it is not necessary that all the curves will have both maximum and minimum points. Number two, we might get 3 points. So again, we have to put each of them separately in the second order derivative to make sure that whether the function is at the maximum point or the minimum point, there are different possibilities. For example, there can be one maximum point, one minimum point according to d2y by dx2 greater than 0 and less than 0, and interestingly for third, d2y by dx2 will be equals to 0, which is called as the point of inflection. That means the point where the function is neither maximum nor minimum but has got some different tendencies. Again, there can be 2 points at which the function is behaving to be maximum and at only one it is minimum. So care has to be taken to ensure that all the values are separately substituted or put into the second order derivative to ensure that whether the function is at the minimum point or at the maximum point, and that's the term maxima and minima for you. Thank you.